super famous. I could probably spend all his time talking about his achievements and stuff. He's member of many academies, the National Academy of Sciences and Engineering, the American Academy of Arts and Sciences. He's a foreign member of the Royal Society, and there are probably other societies they're not important enough to mention. And he's winner of a gazillion of prizes. I mean, he is the David Rumelhart Prize. He has the Allen Newell Award. He gave a Plenary Lecturer ICML. He is the World Laureates Association Prize winner, the inaugural one. It's a big one. He is the AMS Ulf Grenander Prize winner, the John von Neumann, and. Okay. And he also was named as the most influential computer scientist in the world by Science of all areas. Okay, thank you very much, Mike. I'm really looking forward to your talk.
Thank you. All right, thanks very much. It's very nice to be on home terrain. The staff person who's organized this reached out to me and said, will you have any expenses to be reporting? And I thought, man, this is a real opportunity to go onto Uber and get that extremely special, expensive Uber car to bring me from my house to here.
No, it's a flight from Paris and back, Mike. You really...
all right, I'll take you up on that. All right. Okay, so this is a talk for the students in the room, and I'm glad that there's a few students here. It's kind of why do we do what we do? And at least in my career, I'm sort of a blend of a computer science and statistician. It was always clear. Computer science is a good thing, statistics is a good thing, let's just do more of it. And I think that's probably still true, but I think the dialogue about this overall field that we're now calling AI is so horrific. It's just so, so many misunderstandings at the level of government, at the level of, policymakers, to the level of researchers. I think the whole why are we doing this is kind of lost at this point. If you ask the people who have all the money or building these companies, why are you doing it? Well, we're going to solve hunger. We're going to solve, climate change. We're going to make the economy grow exponentially fast. All this kind of insane science fiction-y kind of language that they drop into. So if I were a student, I'd say, what the heck is this? All right, so I'm going to try to give a more sober, what are we really doing kind of talk, and in my own way. So this is the first time I've ever put that phrase on a slide. Everyone is using it, so I have to use it. So I'm going to give my version of it. First of all, everyone in academia thinks all these ideas came from academia. There's some truth to that, but not quite right. If you go back to the 50s, here are three gentlemen that had visions. Cybernetics, Norbert Wiener was a mathematician. His vision was kind of control theory-esque at large scale, and intelligence arising out of control mechanisms. A lot of that really kind of happened. A lot of what we see is definitely in that spirit. This gentleman, John McCarthy, coined the phrase artificial intelligence. I think it was his dream. I'm not sure exactly what it was, but it was kind of a robot thinking with logical symbols in its head. It was the thought in a computer idea. That didn't happen, frankly. But sadly, his term survived, even really this gentleman's ideas were kind of more influential. And I do want to add Douglas Engelbart to the list. He bickered with all of these. They all bickered among themselves. They all hated each other, I think, as far as I can tell. And he said, no, what computers should be doing is not being intelligent themselves. They should aid human intelligence. And obviously, the search engine is a good example. Search engine's not intelligent, but it aids all of our intelligence. And many developments in computer science, I think, are of that flavor. So I do tend to think these guys got it right, and sadly, this guy's terminology won out. Now, I don't really believe that's what happened. Those academic perspectives just informed everything, and we all went marching off and built all those things. What really happened was this thing called machine learning really did happen. And machine learning is really just gradient descent algorithms, make small adjustments to large bags of parameters. And I want to name two names that I think were the most influential here. One is David Rumelhart, who was my advisor. He reinvented the backpropagation algorithm and published a paper on it in 1983. A Turing Award was just given for that algorithm, basically, because Dave died young, and it wasn't given to Dave. I think Dave would have been aghast that something like backpropagation should get a Turing Award. Not a Turing Award, I want to say Nobel Prize, even worse, even worse. He would have been aghast, but such is life. The other one is Leo Breiman. Now, Leo Breiman was here at Berkeley, and he was working on gradient-based algorithms, in a different, it wasn't layers, it was trees, and it was many, many trees. Why I bring him up is partly because what happened in the real world. So circa by the end of 1990s, companies like Amazon were making vast numbers of predictions. So for Amazon, it was critically important to do the supply chain with machine learning. The supply chain is the biggest stochastic control system ever built by humanity. 1 billion products are assembled in various pieces throughout the world, shipped in various ways to arrive at your doorstep, and you're one of hundreds of millions of people within a day. Okay, so you can't, that's unbelievably complex relative to the classical supply chains. And it was all, they realized at that point in time, the only way to do that is take in all the data available on the ships and all the, the strikes in China and the winds in the Indian Ocean, put that all into a big predictive engine and make predictions and then optimize over those predictions. So they built a system to do that. And what system was it? Well, it was random forest, which was Leo Breiman's algorithm. So it was a gradient-based adjust things a little bit. They did this at Amazon, and they realized they couldn't do this on a single computer because they had way too much data, and this bunch of random forest was really big. So they built lots and lots of computers all federated together to do this. That was the cloud. And so the cloud emerged from random forest run on supply chain data at Amazon. Okay, that is never talked about, but that's what happened. I went down there because I just arrived at Berkeley around 1998. I went there and visited, and I was really excited to watch this whole, machine learning being really used at this scale. It was amazing, and they were like, really, this is really working, and it does surprising solutions we never would have thought of. Okay, so that's already how many years ago is that? Like 30 years ago. All right. What I think changed over the years is really just kind of the data sets changed. The second era is also kind of Amazon and similar companies in the back end realized they didn't just have supply chain data, they had transactional data. People like you and I would go do transactions. This was done at vast scale. They could do recommendations. Same algorithms, same cloud. Everything was the same, just the data changed. Big impact on the economy. Huge. The third era is kind of the one that started maybe 5 years ago. What happened? The data changed. Instead of just being transaction supply chains, it was human language. But you still used gradient-based algorithms on the cloud. Now you can throw in GPUs and you can make them even super powered, but you predict things. And it is surprising, avowedly, that predicting the next word in a sentence over a vast corpora can do amazing things. It is surprising. On the other hand, it was already kind of surprising the solutions that were being arrived at even on those kind of problems. Okay, this is all kind of engineering, but suddenly this phrase AI got pushed here and it became more than engineering. It became, we're creating superhumans, and so on. The dialogue started to get lost. To help bring the dialogue back to something reasonable, I think this is the right way to think about it. We're not building superhumans where we take out a human and put in a computer. We're building new federated architectures that involve computers and humans to solve real-world problems. That's really where it's at. And to do that, it's not just a computer science network everybody together problem. It's also an economics problem and a statistics problem. Okay, so in fact, I like this little diagram now, bring it back to academics. There are three ways of thinking that are contributing to all this. And I don't mean just necessarily these three fields, but these ways of thinking that are kind of hundreds of years old ways of thinking. Computer science is kind of algorithms and, formulae, logical, recipes and all. And it is a way of thinking that led to what we have today. Statistics is a different way of thinking. It's thinking about what's in the world and how can I actually get evidence about that even though I only have partial observations and make inferences. Rather different way of thinking than this. If you blend the two, that's what machine learning really is. Okay? In fact, it's really mostly statistics, frankly, with the stuff here is mostly optimization algorithms. Okay? But anyway, that is the blend that we're seeing rolling out today in this era. That's missing, though, almost entirely is incentives. Okay? It has really little talk about incentives. Why should people play this game? It talks a little bit about fairness because things are broken, but it doesn't have a good solution for solving it. Economics people can talk about solutions to problems like that. So you say, well, maybe economics has all the ideas. Did they ever link up with these other fields? Well, yeah, they did a little bit. Economics meets statistics. That's a field. That's called econometrics. There's been Nobel Prizes for that. That's basically time series analysis with causal inference. Okay, so it's analyzing the economy. It's not trying to change the economy. It doesn't have that much mechanism in it. It's more about analyzing mostly for the purpose of macroeconomics, predicting things still. All right, so not much of this. And then what about economics meets computer science? Well, that's a field too. That's called algorithmic game theory. It's mostly the study of combinatorial auctions, which have also changed the world, very important, but almost no statistics in this field. No learning from let's do the auction again and again and have it learn and be better and better over time and be fair and all that. Not much of that. So what I like about this diagram is that it suggests there's something in the middle. And whatever you want to call that thing in the middle, that's where most real world, large scale industry is solving problems that blend all three of these traditions. In academia, rarely do we bring all three of them together. At Berkeley, with our data science, and we have our dean sitting here representing CDSS, I think of CDSS as Berkeley's really good attempt to bring all three of these traditions together. Very hard, because there's a resistance from all of them. They think they already solve all the problems, but they can't. Okay, so let's now talk about, if you do have all those three kind of ways of thinking in your brain, and you look at the current dialogue on AI, what's missing in that dialogue? I mean, there's many things missing, but here's ones that I like to focus on. There's not very much talk about collectives. Okay, it's all about the superintelligence and the one computer, scaling it. In fact, the data that drives all of this stuff is coming from collectives. So it would be nice if we were a little more explicit about that, and how does it benefit collectives? Lack of focus on uncertainty. I'll talk about that in a moment. And I don't mean just a little bit of error bars like in a statistical setting. I mean real uncertainty. John is nodding here because John leads a quantitative finance firm where if you don't really take uncertainty seriously, you lose. And then the lack of focus on incentives. And this has huge implications. It means things are not, people don't participate, you get people lying, cheating, and stealing, and that's only going to get worse unless we start to take that seriously. All right, so what about uncertainty? If you say, ChatGPT, you just told me something, how sure are you of that? It will say something. I tried this out a bit. It will usually say it's pretty sure about something, here's why. And it's pretty good at it. But then if you say, well, wait a minute, there's this other thing, and did you not also read this other article? It'll say, oh yeah, that's right, and then it'll be very sure about that. You can lead it around and change its mind completely. It's totally malleable. It's not doing reasoning or uncertainty in any way that I think we would recognize, right? What it's doing is being very agreeable. Now that's great, but if I had a doctor who was being very agreeable, hey, you just told me I have maybe heart disease, but what about this? Oh yeah, you really have, instead you have liver disease. Oh really? I don't think I'd be very happy. So embedding these systems in our life for these kind of decisions is problematic. And this is a little bit of quantitative evidence of that. I think this slide is probably the best one. Here's estimated confidence from ChatGPT. It either is often saying a 0 or a 1, or sometimes it says I can't make up my mind at all, 50-50. Humans, you want to be on this line. It's not even close to being on that line. All right, and this is not to say it's bad, and what it typically does, if you ask something about uncertainty, it'll say something, because in the past, some human was asked, how sure are you about that? And the human said something sensible. So it's kind of copying that forward. That's okay, that's prediction, but that's not reasoning or uncertainty. Okay, so how do we cope with uncertainty? So I want to make a kind of a very simplified set of comments here. First of all, I've started to add these little diagrams here because I've been giving talks to the public in Europe, and the public likes these diagrams. All right, so it's argued that humans are not very good at uncertainty. I don't think that's really true. I mean, the vast uncertainty that all of us live in, I don't know what's going to happen tomorrow. I don't know what's coming in the next 10 minutes. I don't know about my dinner. I don't know about everything in my life that matters. It's all uncertain. But nonetheless, I get up every morning and I do, I live. And we all do that. All right? And if I was all by myself in the world, God forbid, I would be pretty bad about it. But I'm in the midst of all of you. So if I don't know something, I can ask you because I know that you probably know that, or you, or whatever. And we all communicate. We create science and culture because we're very good at collaborating relative to mitigating uncertainty. Okay, so coming together in collectives just has many, many virtues, but one is that it mitigates uncertainty. Let's think about that a little bit. Here's a duck, nice picture too. Took so long to find that picture and steal it off the web. I'm not incentivized to pay for anything, right? This duck has done a lot of statistics in the past, and it's figured out that 2/3 of the food can be found on this side of the lake and 1/3 over here. It's got very small error bars on those quantities. You throw the duck down now and you say, where are you going to go, duck? And you do this day after day for the next month. What will the duck do? Will it go left or will it go right? Anybody know the answer? This is a well-known experiment in social science. Well, the Bayesian optimal decision, the Bayesian duck, would go over here with probability 1. All right? Do ducks do that? No. They hedge their bets and go over there a little bit, but not just a little bit. They go over there a lot. They go over here 1/3 of the time. Okay, it's called probability matching, and it's viewed as suboptimal. Now, humans also probability match in many, many situations. So, for long eras, psychologists and others tried to explain this. They said, and often the explanation was just that ducks are stupid. Ducks are not Bayesian. There would be a title of a paper, ducks are not Bayesian. But then humans are stupid too. Humans are not Bayesian. All right? And that may be true, but so then you can sort of say, well, this is a exploration exploitation problem. You should always hedge your bets a little bit. Maybe you don't really have the right error bars. But this is 1/3. It's not just a little bit. It's too big to be explained by those phenomena. All right, so what's the right answer? Does anybody know? Or at least, what's the preferred answer by the lecturer? Do you know? There's other ducks. Thank you. Thank you. Ducks don't match. They probably match. Well, there's often other ducks. In fact, we evolved in worlds where there's other individuals. All right, and so even if we're not explicitly thinking about it, that's how we evolved in that world. All right, so if you throw down a bunch of ducks, one algorithm to get a lot of food eaten by everybody is a Nash equilibrium, which is that randomly each duck decides to go over there with probably 2/3 and probably 1/3 over here. That is a Nash equilibrium, meaning highest maximal social welfare, meaning more food gets eaten than in any other algorithm. Now you could design an algorithm where you tell ducks where to go and you do allocation that way. But the randomized, decentralized algorithm works just as well. All right, so this may be a simple point of view, but it is really important, okay? It's really important. We evolved in worlds where we're collective, and we should be living in worlds where collectivity thinking is actually favorable. Okay. So we're in a world where we're all increasingly networked, and we're all having all these information flows among us. So we'd like to think about what is not just the right kind of way to connect things up, what's the IP address of everybody, but also what kind of information flow, how should be analyzed, right? And how do decentralized algorithms do this? We're not going to tell everybody what to do. How is this even possible? Well, we know that if you have these channels, we have more data that can flow, and we can even use computers to analyze the data. We can make better predictions. We can link more broadly. But we also know this leads to social network chaos. All right, why do people want to even connect at all? Maybe all the wrong people are connecting. We're incentivizing the wrong people, the good people are not connecting, quote unquote. And why are not people, what prevents them from lying? Nothing prevents them from lying. All right, so we got to start to bring microeconomics into this picture. It's not just a networking problem. All right, now just one more thing about Silicon Valley before I turn to actual positive ideas here. If you read, a statement by, Sam Altman or Elon Musk or whatever, the people who are now in power, they have this weird fever dream, which is there's going to be this thing on the hill, which is the super entity. It's like a search engine plus, and it will soak up all of humans' data. It'll watch everything. It'll know a lot, and then you can query it, and it'll give you knowledge. It'll tell you the right answer. All right, and that's the model. And then you build this on a hill with vast, energy consumption and so on. And that's the goal of research, is to build this thing. All right. If it weren't sort of so crazy, I wouldn't even put a slide about it. And if it weren't the fact that this is really what's in Sam Altman's brain, I wouldn't even bother, but it is. All right, so let's get rid of that thing. All right, and let's embed in this whole network all the computing, and some of those entities are computers. Who cares? But we're going to embed it, and we're going to embed it with us. And it'll be part of the collective. Okay, now I started giving talks like this about 10 years ago here on campus, or maybe a little less. And I gave a talk over in the history department, and they hated this because they said markets are terrible things. How can you be, telling us that we should have markets? Markets destroying the world, right? And yes, they do, I guess. No, they don't. I mean, they've been around for longer than humans have been around. I mean, there are markets of all kinds, and they power the world. And they have problems, and we have to think about that. But everything has problems. Everything that's powerful has problems, all right? Markets do some very good things. They yield equilibria, which means that you don't just have an optimum, which is whose optimum? It's an equilibrium where everybody gets a piece. Secondly, you reduce uncertainty, as I've already alluded to. Equilibria have reduced uncertainty, okay? They make things more stable. think about the market that brings food into a city every day. I have some tomatoes. I recognize that on that side of the city, they don't have so many tomatoes. I drive over there, I raise my price, and I bring tomatoes over there. Thousands of people make those individual decisions, and it leads to a market which brings food into the city every day. And we now understand a little bit about that, supply and demand laws, but all kinds of other, sophisticated ways of thinking about this. All right, now, that leads to stability. If I need tomatoes, not just because I like tomatoes, I need tomatoes because I'm going to do a pizzeria. And pizzeria needs every single day tomatoes. Otherwise, you don't have a pizzeria. I can guarantee, because the market produces stability, that I can now build my pizzeria. And on top of that, other things can be built. Okay? You can have universities where students eat pizza every day. You can build everything. Okay? So prediction becomes easier, and now, of course, you have failures. And you need to start talking about regulating and all that. Absolutely. But we have this kind of jumping to, we're building these powerful engines, and they're going to solve all the world's problems, to, oh my God, that scares me, we have to regulate it. How do we regulate it? We don't know. All right? The way you regulate things in economics, and I'm not an expert here, what I usually say is, people say, how do you regulate AI? I say, bring some economists in the room, at least have them be part of the discussion. But usually what they say is, well, you got to regulate the level of the equilibria, not the level of the mechanism. Okay? And I've learned enough now to give a whole talk about that. I won't, but that's a very useful way to think. All right, so if we were going to create these new market mechanisms, predictions are not enough. We start to have to use language out of economics, incentives and prices. Prices are ways to decentralize computation. They're good things too. Stabilize things, and utilities. All right, so here's my favorite example that it's been part of my life for 10 years now. I'm in a company that has designed a three-way market that's now thriving. It is a market for music. It's an alternative to record companies. And it has signed up at this point about 3 million musicians who all their music goes to this company. This company masters the music, so it serves these people here. And it aims to serve not the famous big superstar musicians, it aims to regular musicians, people that make lots and lots of music, it's really, really good, and it gets streamed to hundreds of thousands of listeners, but they don't get any money for it. It aims to help them make some money. All right, so indeed there are listeners, there's these people like you and me, but critically, and this is Steve Stout's vision, he's a friend of mine and he's the CEO and he's a legendary hip hop producer in the United States. Every musician knows Steve. He also knows people in places like the NBA, and he signed up the NBA so that the music coming from these musicians is the sole source of music that's being played on NBA website now. So if you go watch a clip on the NBA website, you're one of these people, you watch a clip there, the music is coming from one of these musicians, and it's an open market, so everyone knows that musician is being played on the NBA website. Another brand can look at that and say, I like that demographic associated with that company. I'm going to reach out to that musician and have their music also play on my website, or I'll even partner with them, have them write some songs. That's actively happening right this moment. All right, now, to make this happen, there's a lot of data flowing along all these directions. You've got to figure out what music is the best for each of these demographics, and you've got to organize all this, and you have to have market mechanisms. It's not enough just to make predictions. So we did all of that. So under the hood in this company is a pretty sophisticated, what I would call an AI engine that has market mechanisms together with statistics. All right, and it is working. It is revenue positive for quite a number of years now, and it's scaring the record companies, and it's going international and so on. If you didn't have a three-way market, if it was just two, this would fall apart. It would unravel. And so Spotify does something like the following. They take music from people, they stream it to listeners, and then they make money by selling subscriptions. Okay? They independently do that. They are incentivized to get rid of these people altogether. If they could replace them with generative AI, it would be in their interest to do so. And they try. All right. So it is a data meets three-way interactions among independent agents who are incentivized to be part of this market, and they come together because it creates things, and it will create new things. It'll create, I think, new music and new ways to use music in our daily lives. All right, so that I won't talk more about that. I could get into a whole thing about that, but I'm going to talk about an academic project. It's with Ali Reza Fallah, who was in the room, but I think I suggested he doesn't need to hear me talk again, so he's doing something more productive, in which we're studying three-layer data markets. So this is another kind of market. These are real systems that we're now analyzing. We're not trying to design a new company, we're trying to analyze existing companies. So think about systems where there's users like you and me. We interact with platforms by supplying data to the platform, and we get a service back in return. And a lot of these, say, think payments. This is MasterCard. More data arrives at this company, they can build a better service, and we're happy. So there's kind of a nice little feedback loop here. On the other hand, a company like MasterCard does not make enough money off of this service to stay in business. So the way they often make enough money to stay in business is they sell data to a third-party data buyer. All right, and so they sell. Now, this third party is not trying to get data to make their own service and compete with these. They're trying to get data for another purpose, to do market research. They want to learn what things are becoming popular in some cities. They'll look at the data, all right, to decide maybe let's build a new restaurant in some city. Okay, so great, that's the system, and that kind of exists. But now you can ask, are all the players actually incentivized to be part of this game? In particular, are these users incentivized to be part of this? Well, they lose something as part of this. They lose their privacy, all right? And so now you can say, well, this needs to be regulated. That's no good. Let's have the government come in and insist that a certain level of privacy is achieved. That's going to break this market, all right? Another thing you might do is say, hey, platforms, you guys might want to, guarantee a level of privacy yourself. Just make a decision unilaterally that you're going to do differential privacy. Differential privacy is a mechanism where you add a little bit of noise to data in a controlled way. The data is still valuable, but you're also protecting some privacy. And now you have a choice how much privacy to add. You're not being told to do it, you decide. So suppose that MasterCard says, I'm going to add a lot of noise to data. I'm going to have a very strong privacy guarantee. And Google says less. The users then look at that and say, hey, these guys are protecting my privacy. I'm going to send my data there. Okay? All right, so they get more data. On the other hand, these guys are looking at these two services, and they say, wait a minute, a lot of noise is being added here and not here. I prefer to pay a higher price up here. Okay? So there are interlocked incentives here. But on the other hand, these guys, because they're going more to here, this has a better service. It'll get even more data. And so if these guys care about just quantity of data, they may prefer this one as well. It's not clear what's going to happen here. All right, and whenever you get in a situation like that where it's not clear whether a lot of interlocked incentives are actually operative, people will want to opt in. And secondly, whether this will lead to a working system, you do economics. And the economics here is just to calculate the equilibrium of the system. Now, this is not just a classical economics exercise because it has data in there. And so the data's got to be valued under a statistical model. Okay, so this is exactly a blend of statistics and economics. And you can write down, and we have done that, all the equations of a system like this and solve for the equilibria as a function of various parameters. So more broadly, we are doing this more and more in a framework which is called the theory of incentives in economics. The theory of incentives is the inverse of game theory. So just very briefly, one of the main mathematical frameworks in economics is game theory. It's the theory of strategic agents. There's other economics mathematics, equilibria and so on, but the strategic side of it is game theory. Game theory is a kind of forward discipline. It says, write down the rules of some game, have players come and play the game, and here's the outcomes you'll expect to see. Like Nash equilibrium would be an outcome, right? So it's like studying physics. Here's F equals ma, and we expect for things to drop in a certain way. If they don't drop in that way, we invalidate our theory. Okay? And there's a lot of work in economics to do that, all right? On the other hand, if you're an engineer, you might want to go the opposite direction. You say, I'd like a certain outcome, like a certain building stands up. What equations do I design to achieve that outcome? I go backwards. The inverse of game theory says, here's an outcome I'd like. What game do I design to achieve that outcome? And now the inverse of game theory is called mechanism design, or the theory of incentives, same thing. Now, there's different kinds of equilibria. Nash equilibria are ones in which you have a symmetric game. A bunch of players come in simultaneously and play something, and you see the outcome. The inverse of that is an auction. And there's a lot of auction design based on different Nash equilibria. I'd say that's probably less exciting these days in economics and in game theory. More interesting is what are called Stackelberg equilibria. Stackelberg is that you have agents who have different knowledge, and they're not symmetric, and one of them often goes first and the other one follows. So it's often sequential. Okay? And you might have chains of these things. Stackelberg equilibria are very interesting. They've been studied by economists. Now you'd like to about what's the inverse of Stackelberg equilibria, all right? And that's called contract theory. Okay, so I learned about this about 3 years ago by reading a book about it, and it's changed everything we've been doing ever since. You all know what contract theory is. Contract theory are how you handle asymmetry of information. So if I'm an airline and I want to bring people on my airline, and I like to price the seats, it used to be when I was a kid, every seat cost the same. It's like in a movie theater. Every seat was the same. At some point, that started to not fill in the airplanes enough. They started to lose money, and they started to go out of business. And so some smart person said, no, we can't. What we need to do is to get different prices for different people. Now you think about how you do that. Well, you have an asymmetry. If John walks onto the airline tomorrow, up to the the counter, and says, I need to go to Los Angeles, they'll look at him and say, well, look at how he's dressed. He's surely willing to pay a lot of money. We're gonna offer him a price of $1,000. And John says, no problem. He pays. All right. And then Eli comes up and he's dressed less nicely. They look at him and say, okay, we'll let you on for $100. You'll say, fine, $100. All right. And so they were happy because they sold one ticket very high, and they got the plane full of EECS professors. But what happens the next day is that John will arrive and he'll be dressed like Eli. And you can't make this discrimination. Of course, it'll change. One day John really needs to go to LA. The other day he could really care less. Okay, none of us know that a priori. It's in the moment you think about it. So that Sam Altman thing on the hill, knowing everything and knowing how to price everything and how to, that doesn't exist, because in our own heads we don't even know what to do until we think about it. All right, so contract theory says what we're going to do is that we're going to think roughly about what are these distributions of willingnesses to pay. And it'll change. Different people will have different willingness on different days. But here's a whole distribution it has. What we're going to do is set up a set of contracts, which are service price, service price, service price. And we give that list to everybody, the same list to everybody. Some people will pick that one, some people will pick this one, and people will pick different ones. The mix will then lead to high revenue, but it'll also lead to high social welfare, because everyone found something they like. All right, and long story short, the airline survived because of this mechanism. And weirdly, this mechanism is hardly studied at all outside of a very small branch of economics. So the more general theory is that you have principals and you have agents. So if you go back to this, think of this person as a principal and here's an agent. This person knows something more that this person does not know, but they need to interact. So this agent here will often prepare a contract for this agent here. And the contracts may differ for different services they're looking for, okay? And their goal is to make good contracts so the overall system behaves well. Now, if you do this not adaptively, now you're in the world of economics. You just write down contracts and people in the airlines just kind of change the numbers willy-nilly. A good statistician would look at that problem and say, hey, can I actually learn the contract? Okay, and so that's what our work is about. Okay, so going back to this, that's what we do here. And in fact, in this situation, interesting, the platform is a principal from the point of view of this interaction where this is an agent, but the platform is an agent from the point of view of this thing being a principal. So you can be both in these networks. Okay, so this is starting to head us in the direction of doing that. All right, so we write down some mathematics for these things. It becomes a statistics problem. We did linear regression here, where these guys are trying to learn something from the x's that is represented by theta, and over here you're trying to learn something else. A functional theta transpose y. And now you have a statistical contract theory problem. Okay, and so when you start writing all those equations out, you get these kind of layered equilibria, and they're functions of statistical data, and you can do all that. And critically, at some point, you have to introduce utilities. Who cares about what? Why do they care? There's a long list of utility functions in this paper, and two of the important ones are the user's revealed information to the buyer. Okay, that's the amount of information the buyer is getting out of this interaction. And then there's a trade-off for that buyer. The buyer gets a certain amount of information, but they have to pay a certain price to all the place they're buying for. So that's bad. And then there's a trade-off parameter. So it turns out when we started solving for the equilibrium in the system, that beta was determining everything. Beta is really important. Okay? So we were able to find little diagrams. There's actually two values of beta, beta 1 and beta 2. And on that diagram, we would say if beta is set in this way, you get a good equilibrium, that everybody's happy. If beta is set in a different way, you get bad equilibria. And that's the kind of thing I want to show to a regulator. okay? And we're actually currently doing that kind of thing. All right, so here's some of the details of how you do the equilibrium analysis. You write this down as a game, a Stackelberg game. First, platforms decide how much privacy they want to offer. Users decide whether to opt in or not. Platforms decide a price to charge. And then buyers decide from which platforms to purchase data and so on, okay? And then you solve for the equilibrium as a function of beta and all these expectations over data. We then prove theorems where you can say there exists certain lower small values of beta, certain large values that above beta bar, there is a certain, an equilibrium exists and it has a certain property, which is that all platforms enter the market. If it's below that, then only certain platforms will enter the market, what we call low-cost platforms, the ones that are like the Google-like things, where they don't need this market to be in the system, okay? And now you can compare this to, existing mechanisms like GDPR. GDPR is a privacy mechanism that's imposed by the government. And you can say, what social welfare does that yield? And that's been analyzed quite a bit now. And in fact, there's a recent paper sort of showing how badly it's hurting small firms in Europe. The big firms are not being hurt by GDPR. The small to medium enterprises are being hurt by GDPR. A lot of them are going out of business because of GDPR. All right, and our analysis helps to explain that. And I'm not going to get into details here, but just to say we studied the GDPR full ban, and we say that it only maximizes user utility in a certain setting when all the platforms are low cost. And then our equilibrium allows us to say that in certain situations, a non-uniform privacy mandate actually increases user utility, okay? That's the kind of thing that I've gone to the government in France and talked to them, and they like this language. They say, okay, this is more nuanced than the things that we've been thinking about before. Okay, so there are lots of problems at this interface between CS and economics and stat. I've spent much of my last 10 years working on relations between optimum, equilibrium, and dynamics. But all this stuff here is really where my heart is these days, about these information asymmetries and how do you deal with bias between entities, how do you get systems to cooperate even though they have different goals, and so on and so forth. All right, so in the rest of my talk, let me look a little bit at my time here. I'm going to give you a couple more vignettes of problems that have a little of this flavor, just to give you kind of examples of problems that I think are worth solving and can be solved. And I'm going to skip over this really quickly just to give you a little flavor of each one of these. And there are papers on all of these things that give you a better flavor. All right, so one of them starts with this idea we had with these folks here, all students at Berkeley. Stephen was a postdoc, is now at MIT, called prediction-powered inference. And this is one where there's not really a story about incentives, it's a story about bias, and very, very large bias. And it may be a surprising source of bias. We started by looking at systems like AlphaFold. AlphaFold makes predictions for protein structures. It's really, really highly accurate. You give me a sequence, it'll tell you the structure very, very accurately. It's a collective mechanism. It took data from all kinds of people and all kinds of scientific situations. So there are now many papers that are called AI for Science papers, which are taking AlphaFold as ground truth. So there are still only about 100,000 sequences whose structure is known from lab work. On the other hand, AlphaFold can generate hundreds of millions of proteins predicted structures. So if you're trying to test out specific hypotheses of this protein does this or that, you might just take AlphaFold to generate data because you get way more data than just taking the lab work. So that's the temptation. Here's an example we studied, which is, it turns out, a pretty famous study in protein structure. You're asked whether, so a protein can have quantum disorder or not. Most proteins like to fold up into nice little bundles, but sometimes there's a little quantum fluctuation that leads to strands kind of hanging off, like hair hanging off my head. It used to be thought that might be a broken protein, it's just not going to be used by nature. But these people are asking, maybe it is used by nature. And so we could ask, you could have a little 2x2 table. Quantum fluctuations, yes or no. Phosphorylation, yes or no. Phosphorylation means you're active in the cell. And you could take all the protein data bank and you could reduce to this little 2x2 table. And now you're a statistician and you say, is there an association between this variable and this variable? Is the diagonal bigger than the off diagonal? All right, so you calculate the odds ratio, comparing the diagonal to the off diagonal, and then you ask for the standard deviation or standard error of the odds ratio, okay? These folks did this and they found that the standard deviation was huge and it covered the value 1, which means there's no association. So they couldn't claim there was an association. Someone came along just a couple of years ago and said, forget using just the data that we have available, just use AlphaFold to generate data. Now you got 200 million data points. You run the same, you reduce everything to a little 2x2 table, you calculate the odds ratio, you get the error bar, and you do the test. And now because you have 200 million data points, the error bar is really tiny. You're really sure, and that did not cover the value 1, so they said, yeah, there's an association. This may or may not be the right answer, but it's bad statistics. All right? So here is the odds ratio. There's the formula for it. We redid the whole thing. We took half of the data, and we used that as just complete held out, and we did a Monte Carlo run to get an idea of ground truth. So the ground truth ratio on that half of the data, it seemed like it was about a little over 2. That's there. Here is the odds ratio coming from AlphaFold. AlphaFold is getting a very narrow confidence interval, and it's not covering 1, but it's not covering the truth either. It's very far away from covering the truth. So you're very sure of yourself, and you're very far wrong. You're very biased. This is an extreme bias in the confidence interval. Okay? If you forget about AlphaFold altogether and just go back to statistics 101, here's the confidence interval you get. It's based on 100,000 data points. It covers 1, sadly, so you can't make a conclusion even at 20 years later. All right, the new procedure gives you these green confidence intervals. It's called prediction-powered inference. And it is essentially a way to correct this confidence interval using, it's a way to blend these two, okay? So it uses AlphaFold. It doesn't throw away AlphaFold, all right? But it also adds a little bit of extra data for this specific hypothesis that you have in mind. And that's enough to correct the output of AlphaFold, all right? So these green intervals provably cover the truth, just like this one does. But they're almost always much smaller than this one, and they're not as small as this, okay? We did this in a bunch of domains, and it allowed us to kind of find out what was wrong with AlphaFold. So we didn't know this a priori. AlphaFold is highly accurate overall, but it turns out for quantum fluctuation, it was pretty bad, all right? Here's the prediction for a particular protein. Here's the actual experimental structure. It just missed the quantum fluctuation completely. This wasn't known a priori, but this is what's driving why we get that very biased confidence interval. And I would assert, we did this on lots and lots of other experiments, published this in Science. This happens all the time. Scientists are not interested in the old data, which is what was used to build AlphaFold. They're interested in brand new data that haven't been explored yet. And it's very likely they're going to tumble into situations where it's going to be highly biased. And they don't know that a priori. Look at these nice confidence intervals, and they'll assert, here's the answer, and it'll be based on bad statistics. All right, so I'm not going to assert that AlphaFold is a bad idea at all. I think it's a great idea, but I assert that if you add statistical reasoning to the top of it, you can actually get the best of both worlds. Okay, just here's another example where you can sort of see this phenomenon happening, and then here's a third, final example I really like. Here's one where the machine learning model gave a terribly biased answer, very sure of itself and terribly biased, completely wrong. Here's the new interval, which is not much better than the classical one, but that's appropriate because it's not much power to be gotten out of this method here. So it's honest. It says I can correct that, but I'm not going to overpromise. All right. This is one slide that shows just how this is done. And just to say this is kind of a generalized estimator of a bias in a confidence interval, which is a little bit different than what we're used to. We're used to estimating bias of a point estimator. This gets bias in a confidence interval. So a bit different. And I'm not going to go through the details there. Okay, that project led to another one where we brought in incentives. Okay, so the project we just looked over there was asymmetry of information. AlphaFold knows a lot. It's like the tower on the hill. But I got a particular problem, and I know a little bit more about my particular problem. Can I put the two together? That's what we've just shown that that's possible. All right, now we're going to look at one where there's actually incentives at play, where people have vested interest, not just bias. All right, again, this is Stephen, who's now at MIT. Michael's at Stanford, and Jake, who's at Chicago as a postdoc. Okay, so we studied this in a particular domain, which is clinical trials. You know, just it's a good way to explain the ideas. You can sort of see there's tens of millions of dollars invested in clinical trials every year. These are causal inference experiments. I put 10,000 people in the treatment, 10,000 people in the control randomly, vaccine, no vaccine, and I compare and assert that the vaccine works or doesn't. That's expensive to do. All right, now. In reality, these hypotheses that are being tested, vaccine, yes or no, are not just coming out of nature. They're coming out of a pharmaceutical company that's got a vested interest. I've just designed a new drug. I'd like for my drug to go to market. I did some basic tests to make sure it doesn't hurt anybody, and now I'd like to go to market. I like to make a lot of money. The FDA is sitting and looking at that and saying, well, I'm only going to let to market after I do a clinical trial. And you'll have to spend a lot of money to do that, okay? So you do that, all right? And now the question is, how do I assert control the false positive rate and the false negative rate? That's what the statistician wants to do. A statistician might say, in the simplest case version of this, that if the drug is actually not effective, theta is equal to 0, that the probability of approval is less than 0.05. That's the false positive rate. Whereas if the drug is actually effective, the probability of approval is 0.8, the power. And this is done by the FDA. Extremely good statisticians doing this in extremely daunting situations. The problem is that their hypotheses they're testing are not just ones from nature. They're just not just ones from a scientific theory. They're coming from pharmaceutical companies. So let's think about the pharma's point of view. Let's imagine a case where there's a small profit to be made. It cost $20 million to run the trial. The pharmaceutical companies got to pay that. And let's suppose that if they were approved, they would make $200 million. Okay? The CEO can now look at all these numbers and she can calculate my expected profit. If my, counterfactually, if my drug is actually not effective, it's minus 10 million. Okay? It's costly. All right, so she goes to everyone in the company and says, only send in candidates if you're really convinced they're a good drug. Now, they don't know it's a good drug, but they have some background knowledge. They have some internal knowledge that the FDA does not possess. So they use that internal knowledge to only propose candidates who are likely to succeed, and therefore they're not going to lose money. The other situation, there's a large profit to be made, $20 million to run the trial, and $2 billion if you're approved, ibuprofen or something. All right, here the CEO can do the same calculation. She will find that if the drug is actually not effective, the expected profit will be $80 million. And why? Well, because that 0.05 is not minuscule. If you throw enough candidates at the FDA, a few drugs will leak through and you make a lot of money off of them. And okay, so a drug goes on the market for a couple of years, it's not effective, and who's to care? All right, so is it unethical? I don't know, but it's what happens. All right, and so people do die not because the drug is hurting people, but because it could have been a better drug. All right, now, so that's a problem. How do you fix this? Here the CEO says, send every drug up that's possible, and they will still use some of their internal knowledge, but they don't need to. Well, the way to fix this is to realize this is a contract theory problem. Okay, there is a principal, that's the FDA. They only have partial knowledge, and there is an agent who has private information. They know something about the proteins, the drugs that they're designing. They've worked on them in the past, they know something. And they can't just tell that to the FDA, or they don't want to. Okay? So what does the FDA need to do? It needs to design not just a price, 20 million, it needs to design a contract. All right? And we want to design that contract adaptively so when you put it out there and people actually use it, you control type 1 and type 2 error. Because that latter statement is what's new. You didn't have that in classical contract theory. It's a statistical criterion for a contract. Okay, and so just to say well, we do that is we design it, here's what we call a statistical contract. Agent comes in and opts in or opts out. If they opt out, that's fine. They just walk away. That's part of the mathematics. If they opt in, they pay the reservation price R. Then they're going to pick a payout function from a menu. A payout function is like the terms of the contract. How many cities can you use it? Can you roll it out in for what time? What are the constraints and so on? So parts of the deal. The new part is that you run then a trial from nature. You sample nature and you run the clinical trial. You see what nature thinks, okay? Now, if I had a lot of confidence in my drug, I would have picked a favorable payout function, good terms for me, because I believe in it. And now, when this clinical trial is run, I get the profit. All right? If I didn't really believe in my drug, I would have picked a less risky choice here. Okay? So it's my game is to find enough things that span the risk tolerance and have the right prices for all those things. Okay, so that I control type 1 and type 2 error. Okay, so we run these things, then you have the payoffs, and now you do the mathematics on this. Okay, so again, in this talk, I'm not going to go into the mathematics, but we can solve for the equilibria here, and we're able to design optimal contracts, and moreover, we can even give an if and only if statement. A contract is incentive aligned, meaning that it's in the interest of all the players to actually play this game. No one's just losing money. Okay? Incentive aligned means that a certain expectation is less than or equal to 1. If and only if all the payoff functions are what are called E-values. E-values are non-negative super martingales. It's a class of things in statistics that are used to assert evidence against a null hypothesis. So if we can now go back to the FDA and say, we have a vocabulary that we need to talk. If you want to design good contracts, they have to be collections of non-negative super martingales. And they say, what's that? We can say, well, here's some examples. And you can add them and still get non-negative super martingales. We know how to design a little vocabulary here. Okay, so I'm going to finish up in a couple of minutes. Let me just say a couple more little vignettes here. The most recent areas of focus in my group, and here are some of the people, it's not just in my group, Nika's a faculty colleague, Ben Navasny is a student with Nika and I, Mina is a student with Jacob Steinhardt, and Ali Ray's a postdoc in the group, where we're really trying to take all these ideas all the way to regulation. Talk about market design and regulation so we can actually talk with governments. And so I'm just going to tell you a couple of little vignettes here and then I'll finish. One of them has to do with price discrimination. A lot of people in government care about price discrimination. Should companies be allowed to discriminate in price, or are we doing price gouging? How do we study those kind of things? And so there is a worry that some people get better prices than others. For what reasons, and how do we control all that? And so this has been studied in economics. So there's a famous paper by Dirk Bergman and colleagues where they are studying consumer utility on one axis and producer utility on the other axis. And what the setting is that I have a huge market out there. I'm going to segment the market in various ways. Maybe by geography, maybe by age, various ways. Let's look at all possible segmentations of a market and ask what is the resulting consumer utility and producer utility. And they proved a theorem which says that resulting set of all possible utilities is a triangle in a certain space. This is a very important result. It may get a Nobel Prize itself. This is used by people in policy making circles all the time. Okay? All right, so we came in and said, what about if we have privacy guarantees? And it's very natural in price discrimination. I would like to have price discrimination. For example, I go to the movie theater, I get a discount because I'm a little older. I don't really get it. I feel embarrassed to do that, but I could. All right, so to get that discount, I've got to reveal my age. And so I lose a little privacy, but I get something in return. And in general, that's how this good, efficient system should work. We reveal something, we get something in return. If we just reveal something and nothing in return, who wants to do that? All right, so now I can ask, if I add differential privacy, how does the space of utilities shift? Okay, so with Ali Reza, we did the mathematical analysis of that. I'm not going to tell you about how we did it, but here's the result. The classical triangle shifts down and shifts over a little bit. And it's not even a triangle anymore, it's a convex shape, and it actually is a projection of a high-dimensional polytope. All right? And it has some nice properties. In particular, consumer utility is bounded away from zero. You always get positive consumer utility at the expense of a little drop in producer utility. That's maybe something government people will be happy with. Okay, so I'm going to skip the rest of the details about that particular mechanism. It leads to qualitative conclusions here. And then I'm going to just mention briefly some work with Mina, who's maybe in the audience or maybe not. Mina's on the job market this year, and I wanted to highlight one of her amazing projects. Mina has kind of been leading the group, leading all of us really into thinking about the large-scale market design principles that arise when we do the kind of data-influenced mechanisms we've been talking about. She's working with me and Jacob. And so this is about barriers to market entry. And so this picture kind of tells it all. We're all talking about LLMs these days, and we're all talking about the fact that companies are supplying these LLMs. And now there's a market. I could go to that LLM or this one. And there's a worry among many people, including government people, that it's all going to reduce to one LLM. All right. So then the government could say, nope, it's a monopoly. We're going to have to break it up. But are there also reasons why it wouldn't reduce to a single LLM? And there are, okay? And so one of them is reputation damage. If you're a very big company and you have a glitch in your LLM, you're going to suffer a big reputation hit. If you're a tiny little company that no one's paying attention to and there's a little glitch there, no one notices. All right, so if you quantify that and ask, how does the probability of a glitch relate to the amount of data you have, you can talk about these scaling laws that we're all talking about in LLM world. And you can make a quantitative relationship between reputation damage and size of your LLM. So that's what Mina has done in a very interesting way. And I'm going to just show you, I think I'm going to finish here, but I just want to, let me just go to all this. Okay, all right. This slide I showed in the French government. Okay, this was a bunch of economists in the French government. I was really proud to show this. What this slide shows is that If I have a company, a very large company, it's got infinite data, and I have a very small company that's wanting to enter in, is there any chance it can enter in and still not get killed? Okay? All right, so this axis here says this is the gap, the discrepancy between me as a new entry and the existing large company, okay? If that gap is really, really small, then I need a lot of data to enter into this market, but not infinite, okay? Even it's a very small gap, I can still enter in. I can still survive. And if the gap gets larger, the amount of data I need to enter into this market gets to be very, very small. Okay, so this is a very favorable result for market entry. It's not something you typically see in macroeconomics, but it has to do with the fact that these neural networks have these scaling laws. Okay, and so this is the form of the scaling laws that mean to analyze in the situation. Behind this is some matrix, random matrix theory. And so I said that to the French government officials. They said, "Oh, tell me more about random matrix theory. Is that Marco Parchinker?" Yeah. So these, wow. So anyway, just to say that you can now start to analyze these things, not the tiny little algorithmic details. You can analyze the overall scaling law and put these in as economic entities and start to analyze the effect of this economic entity in the context of an ecosystem. All right, I'm done. Let me just leave this slide, which I used in several talks recently. I think our era is an era where a new engineering field is emerging that is not about a super intelligence that is threatening us all, but rather about all of us being connected in new ways. And that can lead to maybe more effective interactions, maybe money for musicians. It can also lead to maybe new democratic principles, maybe better, healthy world. Certainly, healthcare could improve, a lot of things could improve, but it's all down in the trenches of building this new engineering discipline. And I think it's very much like what happened with chemical engineering. There was chemistry, and then 20 years of effort led to chemical engineering, where you could build factories that really worked. Electrical engineering, you had Maxwell's equations, and then 20 years of effort led to electrical engineering. I think here, too, we have some basic proto-principles of gradient descent and hypothesis testing and all that. And we need about 20 years to start to build systems that actually, for good reasons, lead to human happiness. That's what engineering disciplines aim to do. And I think I am an engineer. I believe that we should be building good engineering systems. In statistics, where it's really my home discipline, it's always an emphasis on science and mathematics. We're just trying to make good mathematics to help the scientist. That's how I was taught. That's what we're supposed to do. But then I saw all of our algorithms out there, like Leo Bryman's, being used in industry to do engineering things. And I said, can't we also design good engineering artifacts with statistics? And I realized that, yes, we can, but only if we start to bring in economics and put it all together. So anyway, that was a rush through a bunch of ideas, but I hope it was interesting to all of you. Take care.
Thank you very much. Does this work? No? Okay.
They can hear you.
Thank you very much. And we have time for a few questions, so I'm sure there are tons.
Yes.
With these economic models that you're using, to what extent are you imposed? So I know in a lot of economic models they impose very strong, unrealistic assumptions. Yeah. To what extent are the strength of the assumptions that you're making in the models that you're using?
Yeah. Thanks for asking that question. It's a good one. I often get it, and here's my kind of brush things under the rug statement. Most economic theory, you wrote down a bunch of rationality of parametric curves. Okay. And then you did some mathematics on all that and I got some conclusions. We're statisticians. We bring in data. And all of our curves are informed by the data. And so to the extent that there's behavioral economics out there, people actually behaving this way, that's actually coming in through the data. Right? So it's a little bit of a glib answer, but I actually believe it. All right? We can throw away many of the assumptions of classical economics because the data inform the functions that are all inside of these systems. That doesn't mean, again, you don't have to think about it. But it means that you're just not beholden to those very, very narrow rationality. In fact, rationality is kind of a classical one. Here, the rationality is just that are you incentivized to play the game or not? That's it. That's the rationality assumption. And if you're not incentivized to play the game at all, that you can walk away, that's fine. If you're not incentivized, but really you should be, there's a real opportunity you're missing here, then we just didn't do the modeling correctly. And we need to add more data. And so we do, but that helps you to understand where you should add more data. But yeah, I think so I don't put psychology and, neuroscience and all on my slides. But I really, behavioral economics is really what, a big part of this story. But I think that's kind of in the blend between statistics and economics. It arises in that blend. Partly, not only. Yeah.
You said that the United Masters triangular market is necessary to keep it from collapsing. Why is that necessary, and why doesn't it collapse even with a triangle?
Yeah. So we wrote a whole unraveling phenomenon. It's called unraveling, and so if you remember in economics, there's this Market for Lemons paper that was very famous. It's basically that kind of analysis that shows that this market will unravel. And it's just based on particular ways we wrote down the kind of Spotify model, that the only way for that model to survive is that if they do advertising or charge subscriptions. In our more endogenous organic model, where the only money coming in is via the willingness of the brands to pay for a product that is in their interest, then the market does not unravel.
So the only money in that triangle, it's not the individual consumers don't pay for anything.
Individual consumers don't pay. Now, I would love individual consumers do pay. I would pay, I would pay for YouTube. Sadly, the Google and Facebook and all, people decided everything should be free, and I think that's been very distortionary. But I've talked to all those people and say, why don't you fix this? They say, oh, yeah, we wish we could, blah blah blah, but they don't. So I don't believe they will. So that's why I got involved in this company in part to part, is say, here's another place where money will come in, and it will actually stabilize a market, but it is not based on advertising at all. And indeed, so the money has got to come in somewhere, and here the money comes in from the brands having something that's valuable to them, that great music that a lot of young people really like is being played on their website for a particular purpose. Totally, the brand managers are all in on this. And so I want to find more mechanisms like that for other domains. Eli.
So I finally got an insight into why you moved to France. It's the bureaucrats that you're dealing with in France are all graduates of École Polytechnique. They actually understand the math.
They do. You hit on it. That's absolutely one of the reasons I'm in France. I think the dialogue here in the United States is completely broken. The West Coast people are all crazy, the Sam Altmans and all that. And let's not even talk about what's happening on the East Coast these days.
But I have a specific question, and that is that at the beginning of your talk, you gave a little historical wrap-up of where all this stuff came from, and you went back to 1990. And it frustrates me a little bit that people think everything came out of backpropagation, when in reality, it all came out of operations research and linear programming in the 1950s. And I wonder if you have a comment on that.
Yeah, I don't really. I mean, it's totally true what you just said. When I put Norbert Wiener up there, he was, of course, part of that revolution. And I believe that era, the 40s and 50s, was critically important. It led to linear programming and nonlinear programming and all that. Where they kind of got it wrong is they weren't being statisticians. They didn't realize that the objective functions were often sums over vast numbers of things, and stochastic methods would prevail. So backpropagation is both gradient descent, but it's also critically stochastic gradient descent. Now, that was also anticipated in the 50s too, by people that are, mostly in math departments and statistics departments. In fact, Jack Kiefer, who was here, wrote one of the first papers on stochastic gradients. But anyway, yes, really, at the end of the day, people often ask me, who's going to dominate in AI? And I say, well, AI is basically gradient algorithms that everybody knows, and the archive is full of every new last idea and trick on this. It's not that you can have any country dominating, because every student in every country can read it immediately, and it does read it immediately. But yeah, I don't know if there's any operations with search people here, but they kind of were winning everything. In the 40s, 50s, they were dominant, and they kind of lost it somehow. And I think it's time for them to come back in, perhaps, but. And I think a lot of these fields kind of lost because they didn't have statistics in play. They did not think about how to analyze data and think about causal inference and think about uncertainty and all that. And then statistics, lost it because they didn't really want to think about these big scale issues.
Okay.
More questions? Yeah.
So follow up the earlier question,
Yeah.
Does it make sense to have 4-way market or 5-way market?
Yeah, it's a great question. It does. And I think it's a very creative thought to start to put together multi-level, multi-tier market principles that are data markets and so on. And So yes, a couple of my students in the room here are definitely thinking a bit about that, but I think it's absolutely we're going to start seeing that. We're going to also see brokers arising. I think between a lot of these entities that provide these services and those of us who use them, it's too big of a gap. There's going to be all kinds of brokers arising. I think there'll be all new interesting ecosystems arising, but they won't be classical. They'll be kind of new statistical agents. Yeah.
Okay, I think we should leave it at that. It's 1:15. Thank you very much, Mike.